Is this now better?
Yeah.
Okay. Yes. All right. Good. So I guess there's no good headphones for my laptop, I guess. All right. Let me share the slide with you. Okay. And okay, so just reminders, this modular arithmetic sessions that sort of was crowned with these cryptographic applications, that will be subject of a test on Thursday, not Thursday, Monday, after Thanksgiving. And there is a batch of exercises. It's called homework 7. And there is also a practice, like a test review, practice test. The type of exercises are all should be roughly of the same type, and so so I think you have the material to go over, and of course there is also exercises in the iBooks, extra ones. If you have some questions about these, because you might, right? There's, for example, different versions of the fast exponentiation algorithm. There is all sorts of questions possible about modular arithmetics, or the terms, or whatever. Post them on Piazza and try to be active to get these issues sorted out and help everyone else in the class as well. This is chapter 9. Yes, the test is on chapter 9. Essentially, test 3 equals chapter 9. Okay. All right. Let's go then to chapter 10. Yeah. Different stuff. The last segment in the class, except that I'll try to extend it at the end and to probability. And that's not chapter 10, but chapter 11. But I'm not sure that we'll have much time for this last extension. Possibly I have to leave it off for you to make that jump and read the first few sections of chapter 11 and see how this applies and allows you to well, it basically lets you compute probability of some events that you will commonly come up in a life of a computer scientist / engineer. Okay, so let's see. So for first, so we'll be basically dealing with something called the big name is combinatorics. So what is combinatorics? What is counting? So we have different sets, and we want to count how many elements of the sets are there, and this will be. And then there's different ways of counting based on the nature of the objects that you're counting. Are these ordered objects? Are these unordered objects? Are these subsets, sequences, some subsets and sequences with some constraints? Like, for example, so it's a sequence, but well, it's a subset, but well, okay. So there will be sorry. There will be other constraints that are thrown at you and make it more complicated. It's not just subsets and sequences. And we'll see when these come up. So So that's why it's very relevant to in CS, where you need to be able to understand like what fraction of inputs have certain property, and how to count number of objects that are being generated, or number of possibilities for different classes of inputs, and on and on. Okay, so here is the first rule for counting. It is if basically it's a rule for counting number of sequences. So here's whose elements are members of some sets. Okay, so think of three sets. Sets of possible sandwiches, it has three possible elements. Sets of side dishes, 2 elements, and set of drinks, 4 elements. And let's think of a lunch as a selection of each of these three. In other words, it's a sequence whose first element is in the sandwich set, the second is in the side set, the third is in the drink set. Right? You can think of this as a record data structure. And the question is, how many possible records, how many possible records do you have if these are your domains? So this is lunch is a sequence, and the product rule says that the number of such possibilities is you just multiply the cardinalities of these three sets, right? And indeed, if you have 3 choices for a sandwich, 2 choices for a side, and 4 choices for a drink, you have 24 choices, 24 way of ordering a lunch, right? Because the lunch is a unique sequence in this Cartesian product of these 3 sets. And so that's a basic rule, right? Like you have a bunch of sets, and you consider a cardinal product of them. And how big is this cardinal product? Well, you know that already. It's the cardinality of each of these sets multiplied. And what is the cardinal product? What is that object? Well, it's a set of sequences of length n, whose first element is in class A1, second element is in class A2, etc. Right? So I will use words like class, domain, okay, but for a set, it's just they mean the same thing, but it might be more context convenient. Okay, so this is what's happening in general, and another way to see the product rule. So for how to count sequences, the number of possible sequences like this, in other words, how to count elements in this cardinal Cartesian product, is you can think of this as a process. A process of choosing such a sequence consists of first choosing one element here, then using element here, etc. Right? And it's basically like a big tree of choices. There is A1, cardinality of A1 choices on the top level. Then there is cardinality of A2 choices, the second level, and so forth. And you can ask how many, so this is a big tree of choices, how many leaves this tree has? Because each leaf will correspond to a unique path from the top to the bottom, and a unique path means there's a unique set of choices. So you end up with a different sequence, right? And that's another, and it's clearly this many choices, right? And this many leaves. So in case these trees are binary, these sets are bits. So all the only choices you make are bit choices, 0 or 1. What's the cardinality of here? 2 to the n number of leaves in a full binary tree of depth n. Okay, so let's say that, okay, an example. You have student council has to have one representative exactly from each class, and there's 5 classes. Let's call them CI, right? So there is a class C, there is a set C1 of kids in the first class, C2 kids in the second class, etc. Right? So how many possible student councils? This many, because multiplication of each of these cardinalities. Why? Because student council is a sequence in this set, in the Cartesian product of these sets, right? A student council, the first person, so however you order these guys, but you will order them by, first is the representative that belongs to C1. Second is the representative that came from class C2. Okay, and so a council is a sequence in this. Well, it's a sequence, right? Whose first element is in here, second in here, etc. And of course, you know that a cardinality of Cartesian product is the multiplication of cardinalities of the sets that makes this Cartesian product. Okay, so here another example. If an athlete, she has an exercise schedule for a week, okay, and each of the exercises on her schedule is run, swim, or bike. So it's 3 choices each. So how many possible of exercise schedules? Where is a sequence of how many elements? 7. Each of these elements is a member of what set? The 3 element, sorry, I cannot make 3 fingers. 3 element set, run, swim, bike. Yes, so it's 3 to the 7 because it's this 3 element set multiplied 7 times. Okay, so an exercise schedule is a sequence in C7, C to the 7, right? It's set C multiplied 7 times by itself, right? Okay. Just like, you know, by the way, how many integers can you represent in base 3 and using only 7 characters? Base 3. And it's the same, 3 to the 7, right? Because this run, swim, or bike, it's a 0, 1, 2. It's a 3 possible digits, which are possible base 3. And you have 7 of these digits. 1 digit for Thursday, for Monday, 1 for, you know, there's a Monday digit, Tuesday digit, etc., to Sunday digits, 7 digits. And how many numbers can you represent? 3 to the 7. It's the same question, right? So you've already seen this question, basically. Yeah, it's just a different, okay, different cast into the different type, but it's exactly the same question. So Chev has a school plan for lunches, and the plan involves 20 lunches, and there is 30 possible meals at every lunch. Okay, so what are we talking about? It's a sequence of length 20. So it's 20 characters chosen from which alphabet? Each character is chosen from an alphabet that has how many possible digits? 30, right? Because every character is a meal and there are 30 meals. So there is a meal for day 1, meal for day 2, meal for day 3, right? There are 20 of them. So how many integers can you represent using base 30 arithmetic and having 20 digits, 30 to the 20, right? And by the way, when you represent integers, the highest is 30 to the 20 minus 1 because you start from 0. Okay, so this is the number of them, but the largest is that one minus 1, right? Because you start from 0. So that's it's irrelevant here, but like if you think of this as integer representation base in a different alphabets, in different bases, right? Okay, so okay, so that's what I was talking about throughout. If you have a set of symbols sigma, and it is an alphabet, so it makes sense to call such a thing alphabet, right? And we want to make strings of length n over this alphabet, meaning any string whose characters belong to this alphabet set are okay. So what's the product rule? It's simply this. Sigma to the n is exactly a set of strings whose length is n and whose every element is in the sigma. And what's the cardinality? So how many such strings are possible? Well, it's this many. Number of elements in sigma to the power of n. Okay. And so clearly, this is exactly what we're talking about in different base systems, counting systems, right? Binary, base 10, base 16, base whatever. And what would be the base here is the cardinality of sigma. Yes. So, how many binary strings of length 4? Okay, the alphabet is just bits, so its cardinality is 2. And because you take a sequence of length 4 over this alphabet, it's 2 to the 4, 16, right? Okay. Okay, so now that was a product rule. Sum rule, a very different thing. Let's say you have a bunch of finite sets, and the objects that now you want to count are not sequences whose first element is in the first set, second in the second, etc. They're rather objects in the union of these sets. Okay, so how many objects there are? Well, the number of elements in the union. And it is easy to count a union of sets if the sets are pairwise disjoint. So if there is no one in the intersection between any two of these sets, right? So then it's clear that in order to count a union, you just have to count elements in the first set and element in the second, and etc., and then add. If there is a non-empty intersection of any pairs of sets here, then you will be overcounting elements, right? If there's 5 elements that are in the union of A1, if they're both in A1 and in A2, then you will count these 5 elements here, and then you will count them again here, whereas these are the same elements of the union. Okay, so we'll get back to this, and it's called inclusion-exclusion principle later on. What happens? How do you count when these intersections are non-empty? Okay, so for example, you have a lunch who's now, okay, we have the sandwiches and the sides, but let's say we have hot drinks and cold drinks. Okay, and we say that it includes a sandwich side and a drink. So a drink is a union of these two. And other than that, it's the same as the previous example, right? So, but importantly, the union of these two sets were non-intersecting. So drinks is just the sum of how many hot drinks you have and how many cold drinks you have, and that's a sum rule. And it's also important that a selection involves an element from the union. It does not involve a separate element from here and a separate element from that. In other words, you don't order both drinks, both a cold one and a hot one. You order one of them. And of course, once you make it by the sum rule, then the picture is as before, right? So it's as if you make a tree of choices, and it's sandwiches, 3 choices. Now sides, 2 choices, and now drinks. And the drinks is, you can split your choice into hot drink or cold drink, but it's on the same level. It's the same decision. You cannot make both. You don't make them sequentially. First choose a hot drink and then choose a cold drink. You make one decision, first which of the two sets, and then which set would, and then after you made that decision, which element you take inside. But you're going to represent that choice by just take a union of these two and simply treat them as a single set, right? And a choice within that single set. Okay, some examples. Well, let's say you have a set of digits, call them D, it's a base 10 digits, and a set of letters, L, 26 letters, right? How many valid passwords there are? If a password is a string over that is composed either of digits, so every character is either a digit or a letter, and there is 7 such characters. Okay, there seems to be no constraint about any dependencies between characters, so each character is chosen independently, and each character can be chosen from either a digit or a letter. Okay, so it's 7 choices, and each of the choices is a choice in a union of these two sets, right? So you can think that it's a 7-character string over an alphabet sigma, which is a union of D and L, right? And the D and L are not intersecting, so the cardinality of this new alphabet, the alphanumerical alphabet, if you will, is 26 plus 10, right? So you're making 7 choices over an alphabet who has 36 members, right? What about passwords? Okay, it's again as before, so it can be, any character can be either a digit or a letter, but now you have a constraint that it must start with a letter. So now the decision tree is that the first character you choose. Again, you choose characters independently. That's the only way you can use the product rule. The choices on level I are independent from the choices you made on level J. Okay, so does not matter how you chose the first digit of the password, character in the password, that does not influence how you're making your choices when you choose the third character. But the first character is now chosen from a smaller set, just letters. All the others are chosen from a larger set, the sigma, a union of D and L, right? So what's the cardinality? It's the sequences now are sequences, the passwords now are sequences over the first character has to be in L, all the remaining 6 are in the union of digits and letters, right? And so cardinality of that is the following, right? Okay. Okay. Let's say that you have a choice, 6 or 7 or 8 long passwords, right? And you're trying to count how big is that space of possible passwords with such constraints. Excuse me. So, well, maybe you can have different ways of counting this, but here is one way. Let's have the top decision be, are you doing 6 long, 7 long, or 8 character long password? These 3 sets are graciously non-intersecting. So a password, there's no intersections between 6 character passwords and 7 character passwords. They're different objects. So great, so we can count them separately and then use the sum rule to just sum the 3 sets, right? And this will give us the sum of the union. So, and now we know how to count each of these individual ones, right? It's the alphabet, the cardinality of the alphabet, which is cardinality of V plus cardinality of L, to the power of the length. So now my objects, passwords, are elements of the following set. It's a union of sequences of length S over this alphabet, and sequences of length 7 over the same element, and sequences of length 8 over this alphabet. Okay, so I count their cardinalities the same way as I did before, individual ones, but I have to now sum them up, right? Because of the top level sum rule that will be used. Okay. So let's say you have binary strings of length 10, but you have a constraint. First and last bits are the same. How big is this set? Okay. I don't know, some okay, nobody chips in. Okay, people chip in. No? B, yes, right. Good. Okay. Why is that? Because you have 9 unconstrained choices for the first 9 digits and no choice about the 10th digit, right? The 10th digit is determined by the previous ones. So yes. So it's just a number of 9 digit bit strings because the 10th digit there's no choice in it, right? What happened here is something can be generalized like this. Let's call it a bijection rule. Okay, no, not let's call it. Actually, it is called a bijection. Sorry. So say you have some element that is hard to count. Okay, perhaps the previous one was not really such a hard example, but still there will be others. If you can find a set such that a set Y such that the set you have to count, whose cardinality you have to count, X, that there is a bijection between the two. Okay, and perhaps this other set Y is easier to count. So that was the element. The Y in the previous example was all 9-digit strings, 9 bit strings of length 9. X was bit strings with length 10, but with a constraint that the first and last bit are the same. And there is a natural bijection between the two. Therefore, the two sets have to have the same cardinality, right? Because what is a bijection? It's a function that is onto and one-to-one. So therefore, if you count y, if you can enumerate them from first to last, let's say there's n of them, and then the bijection, right, because bijection is invertible, so when x is mapped to y, that also means that there is a bijection, the inverse of f, from y to x. So this enumeration from first to nth of all the y element creates some enumeration of all elements in set x, and therefore there must be also n elements in set x, or otherwise it wouldn't be a bijection, right? If anybody was missed, or if everybody was counted twice. So what is the okay, here's another example. So I think I had a slide with, okay, so I think I killed it or something. But what is the bijection in this slide, in this example? The bijection is simple. You take a 9-digit string and you create a 10-digit string. How? By copying the first digit and attaching it at the end. It's a function that maps 9-digit strings into 10-digit strings. Okay, check. The domain and range at least check out. Is it a bijection? Okay, two things. Is it does it have collisions? Is it one-to-one? No, because if two 9-digit strings were different, then when you copied their first bits and put them at the end, the output is still different. So you didn't create a collision. So it's not colliding. Did it cover all bits strings in S10? Well, yes, it's by definition of S10. It's like it's some 9 digits followed by the copy. So inverses always exist. So that's it. That's a bijection. Of course, you know, it just replicates like an intuitive argument that you can sort of see, but it's just a formalization of it, that the two sets are have the same cardinality. Okay, here perhaps a more sophisticated example. Okay, you have a set of n elements, and recall that p, call it x. Recall that p of x is the power set. So of x, meaning number of different subsets. Okay, in this element. So the size of the power set is the number of possible subsets of set x. Okay. Now consider the following bijection between the power set of x, meaning the set of subsets of x, and n-bit binary strings. Okay, so this is the domain, subsets of x, and the range is n-bit strings. If I can show you that this is a bijection, then in order to count the subsets, I just have to count this range, right? So number of bit strings of length n, and that I already know, it's 2 to the n. Here is the bijection. For every subset in X, the bijection will tell me a string, would give me a string, and this is called a characteristic string. And I'm so sorry, this is a typo. This is X. Okay, this thing is no, sorry, Y. Yes. This bit string is called characteristic string of a subset. It's formed like this. The ith bit of the string is 1, even only if the ith element in set X is in the subset. It's a characteristic string for the subset because that string tells me, basically the bits of the string Y tell me The first bit basically tells me, is x1 in the subset? If the bit is 0, then no. If the bit is 1, then yes. The second bit tells me, okay, what about x2? Is that guy in the subset? Yes, no. So that's the interpretation of these bits. So these bits can describe a subset. So take some subset. Let's take a string of 7 elements, right? And a subset here is ABF. That subset is going to be mapped into this string. The first bits are 1 because A is in it. This bit means the B is in it. 0 here means C is out. This 0 means D is out. This bit E is out. F is in. G is out. Okay, etc. This representation of subsets as bit strings is a bijection. How can you convince yourself that it's a bijection? Because if there's any difference in these, if two subsets are different, then there is some element that belongs to one and does not belong to the other. That means that there is some position here that is 1 in one string, 0 in the other. Okay, so it's not colliding. Is it onto? Is every possible bit string possible? And that's easy to see too, because there is an inverse map. Every bit string corresponds to some subset, because the bit string just tell me, take someone, don't take them, don't take them, right? The bits here. So that there is an inverse. That means it's a bijection, right? And of course, we knew that the power set of set X, its cardinality is 2 to the power cardinality of set X, but here is a proof of it, right? If you remember this recursive algorithm that generates all elements, all possible subsets, then just by, if you can argue that this is a correct algorithm, then you can convert this argument into an argument that the way to count of possible runs, which means possible, you know, how big the, yes, it's 2 to the possible, because the algorithm made a choice, one element in the set at each recursive call. So it was yeah. No, sorry. Okay, you know what? Sorry, take it back, because it was a non-deterministic algorithm, so the many traces of it actually could create the same thing. So you know what? I'm sorry. Scratch that part. Anyway, this is a proof that that the power set cardinality is 2 to the number of elements in the set. And a very useful representation of subsets too, right? If you have if you represent sets as subsets, as characteristic strings, you can make some computations very fast. Intersection of two subsets is computing an end of these binary strings, right? Bitwise end. A union is a bitwise OR. Okay. Here is another example of a bijection rule. Let's say P6 is a set of binary palindromes of length 6. In other words, these are six long bit strings that have the palindrome property, which is that if you read this bit string left to right, and then you read it right to left, it's the same bit string. Okay, so if you take your bits and then you flip them, you have equality between the two. Okay, so how many such bit strings are possible? Well, here is an easy bijection between the set of all bit strings of length 3 and set of such palindromes. The bijection takes a bit string of length 3 and outputs a palindrome of I don't know what happened. Do you guys still see the screen, or did I mess up?
We're still able to see it, Professor.
You showed the screen? Okay.
Yes.
Oh, great. Thank you. So you take a bit string of length 3x, and you concatenate x with the same string x, but in the opposite order. Let me read. Okay. Okay. So that's, I call it x to the r. It's a reverse of x. Is this a one-to-one function? So first, like the domains and range check out, right? You're getting, okay, clearly you're getting something of length 6. Are you getting palindromes? Yes, because of the definition of what a reverse is, right? Like it's the same string x, but read backwards. So you can see that it's a palindrome. Do you get collisions? Okay, can you create the same palindrome this way? No, from two different strings x, two different arguments, x and x prime. No, you can't, right? There cannot be a collision. Are you getting all palindromes? Yes, right, because a palindrome has to start, the first 3 digits has to be something, and then the rest is the deterministic function of these 3. So this tells you that you can just count this set cardinality instead of that one. Oh, by the way, in the previous slides, I added like the bijection was from the set I wanted to count to the set that was easy to count. Here the bijection is opposite. From the set it's easy to count to the set I want to count, but that doesn't matter because a bijection is by definition invertible, so it doesn't really matter which direction your bijection goes, as long as it's a bijection that between the easy to count set to the target set that you want to count. Right? So therefore, the number of palindromes is the number of binary strings of length 3. This an easy sort of variant of this says, okay, this will generalize to every even length palindromes, right? Whether you have 4 elements, 8 or 10 elements, they are flips of each other. What if there is a odd length? Okay, but that is not a big variant. It's easy to generalize from this. Okay, so I finally have that slide I skipped. Okay, I didn't know what happened to it. Okay, so yeah, so what is the bijection here? And it's this one, the string. In order to map from 9-digit strings to the strings of length 10, whose last bit is a copy of the first, I just performed this action of taking 9 bits and copying the first to the end. And that's the bijection. Let me generalize this. Okay, it's not exactly general, but yes, it's a form of generalization. K-to-1 rule. So here's an example. Let's say you want to count kids at a party. They all are like jumping on top of each other, sleeping in some unholy, bundles, and because they move around while sleeping, they thrash about. So you cannot count them, but they all took off shoes, and of course the mess, how many shoes there are, they're all mixed up, but at least like they're in some sort of big box. Okay, just count the shoes and divide it by 2, and that's how many kids you have. Yes. Okay, easy solution. What happened here? It's a case of a so-called K-to-1 rule. let's say you have different sets, okay, kids and shoes. One of them is hard to count, the other is easy to count. And let's say that the function is not bijection. It has collisions. So the same, so in this case, actually, sorry, X is the set of shoes, Y is the set of kids. So X is the easy to count one and Y is the hard one. The collisions will be that the two different shoes map to one child. Okay, that's a collision in the function. But let's look at this. This is called pre-image, okay, of the function. So if the function was one-to-one and onto, this could stand for an inverse function. But even if the function is not one-to-one, we're going to have a notation for an inverse, but it's just defined differently. It's not an individual element, unique element X, that necessarily maps to Y, which is the case if F is bijection, but it's a set of arguments who map to Y. This set might be empty. That's the case of F, which is not onto the range. So some elements in the range are missed. They have no pre-images. So this set is empty. Perhaps they have more cardinality of these pre-images is more than one. That's a case for a function which is not one-to-one. So there is two different x's that map to the same y. So the pre-image of y is a set of cardinality greater than one. I call this function k-to-1 correspondence. If these pre-images sets have a fixed k cardinality, does not matter on every element in the codomain. Okay, so it is an onto function. Every child has some shoes, and it is a regular, k-regular function, meaning every child has exactly two shoes that are mapped to it. Okay, if that is the case, then you can easily count elements of y. Once you count elements of x, just divide them by k, right? Because indeed, if you have the space x, okay, that is somehow easy to count, and you show the k-to-1 map from x to the smaller set y, where k-to-1 means that every guy in y has exactly k pre-images. Well, then if there's n elements in the domain, then there must be n divided by k in the codomain. Okay. Do I have a time for an example for this? Okay, yes, maybe. So let's maybe look at the same example and now cast it as a case of a 2-to-1. So perhaps instead of counting 9-digit strings, I count 10-digit strings. And this will help me to count these strings with a constraint. There is a 2-to-1 function, a natural one, that takes any 10-digit string and outputs a string with this constraint. And it's a 2-to-1 function, so we have collisions. In a sense, you take the 10-digit string and you kill off some information in it by forcing the result to be in this to satisfy the constraint. Which of these functions is it? Okay. Yes, it's this one. It's this one, right? That's a function that takes something from S10 and ignores the last bit and just takes the first bit, with my fingers, and moves it up there. You can think of that. That was sort of very close to the function we thought of before, but we thought of this as a function from a 9-digit string to a 10-digit string with this constraint. But let's just now think of this as a function from a 10-digit string, which kills off the last bit and moves and copies the first there. It's a function that again hits the domain, creates the same objects, right, into domain. These objects are in S10, and it is 2 to 1. Easy to see why, because it kills off the last bit. So, you know, whether this bit was 0 or it was 1, the value is still the same, and there is no other possibilities, right? So therefore it was a 2 to 1 function. It is not the most maybe natural way to count these things. The previous one was faster, but it is still a good one. Okay, and we will see examples where, like, I don't know how to count, and then the K2-1 rule will kick in. Actually, will help you out. So let's end here. Let's not do anything more. You know, this is the overview of what we did. Okay, and any questions? And also, you know, if you want to just talk about something else, we can. Perhaps let me know if you want to stop recording. So this stuff will not be on the test, no. But this week material, yes and no. Monday, yes. Cryptography. Monday was the cryptography stuff. It was the end of chapter 9. On the test, it's part of chapter 9. Today is chapter 10. It's a new stuff. Okay, hold on a second. The questions now are go fast. RSA will be, yes, the RSA stuff was from Monday. It will be on the test. Note, it's in the homework 7. It's in the test 3 review. And test 3 is on the whole of chapter 9, which includes the crypto stuff towards the end. Okay. Somebody says, what are your thoughts on the coverage overall? What do you mean by that? The test is on Monday, so after Thanksgiving. And so the person who asked, what are your thoughts on the coverage overall? If you're still around, you can just say what you mean, unless we answered your question already. Okay. I mean the class pace and what material we might have after. You know, I feel like maybe I'm one lecture behind. I think I am. But okay, so, you know, we will just, yeah, so what will happen towards the end? I will either perhaps not do everything that is in chapter 10, or I will skip asking you to read about probability, although I wouldn't like to do that, because I think that even though we don't get to probability, it is really a very good time, like once you go over the stuff, to do a little jump further and read up like how all of this is reflected in probability. This will help you later on. because you will already do this jump in reading. Not, it will be just part of reading. It will not be part of the test. Okay, and somebody asks if I got their email. Okay, so I think so. I vaguely remember talking to them, but I will check right now. And let's see what's this about. Okay, so yeah. To this person, I want to name them because it's being recorded. I don't know, but anyway, yeah, I will right now check the email and follow up on it. Okay, so and everybody else, happy Thanksgiving, and take a break. Although also, I'm sorry, study this stuff for the test. Okay. And maybe do it sooner than later. Okay. Take care, everyone. I will be still monitoring Piazza, of course, and etc. So you can ask me stuff there. Bye.